Buenas, ¿qué tal? Soy Lucas Ferrarini, responsable del Zorro Azul Estudio en la ciudad de Rosario, Argentina. Este video pretende explicar cuestiones fundamentales del audio digital. Es subtitulado un video interactivo que venía en un software del año 98 y que, como ha pasado algún tiempo, contiene algunas imprecisiones. Para ser justos, contiene imprecisiones también por el hecho de ser un resumen, un primer vistazo. Van a ver unos gráficos pixelados y un tanto inocentes. Sin embargo, considero que está bastante bien hecho y que uno puede darse una noción bastante clara y correcta de lo que es el audio digital. Antes de empezar, quisiera hacer un par de salvedades. Todo tipo de almacenamiento, sea de audio, video, imagen, etc., conlleva algún tipo de pérdida o alteración respecto de la fuente original. Estudiar esas pérdidas a veces puede ser un asunto complejo y extenso. Tanto en imagen digital como en audio digital es muy fácil comprender qué es lo que se pierde y cómo se produce esa pérdida cuando se hace el almacenamiento. Eso contribuyó a la creación de múltiples mitos acerca de la calidad del audio digital y de la calidad de la imagen digital. Comprender las cosas a medias no es un problema en sí mismo, sino que es parte de un proceso, pero puede generar este tipo de inconvenientes. En este video se va a ver claramente de qué manera el almacenamiento digital de audio produce error y no qué errores conllevan las diferentes formas analógicas de almacenamiento de audio. Porque este video se trata de audio digital y apenas menciona algunas de las formas analógicas de almacenamiento de audio. La intención no es analizar mitos ni entrar en una discusión que ya está resuelta, ni mucho menos ayudar a sacar conclusiones aceleradas en base a muy pocos datos, ni muchísimo menos alimentar algún troll. Más bien pretenden ser los primeros datos para una persona que quiere comprender el audio digital. El video va un poco rápido, pero es muy gráfico y están los subtítulos debajo, así que recomiendo pausarlo, mirar el gráfico, leer y retroceder si es necesario. De modo que funciona un poco como material de estudio más que como un video que se ve una sola vez y de un tirón. Este video estará en constante revisión y estaré atento a las correcciones que haya que hacerle según me lleguen comentarios y aportes, bien intencionados y justificados. Empecemos.
Understanding the fundamentals of sound itself is the first step in learning about digital audio and sound. Sound is created by vibrations, such as in a guitar string, vocal cord, or speaker cone. These vibrations disturb the air molecules near them, forcing molecules together, raising the air pressure slightly. The air molecules that are under pressure then push on the air molecules surrounding them, which pushes on the next set of air molecules, and so forth, causing an area of high pressure to move through the air. When these pressure waves reach us, they vibrate the receptors in our ears, and we hear the vibrations as sound. When you see a waveform that represents audio, that waveform represents these pressure waves. The zero line in the waveform is the pressure of air at rest. When the line swings up, it represents higher pressure, and when it swings low, it represents lower pressure. This waveform is the equivalent of the pressure waves in the air below. The amplitude of the waveform is the change in pressure from the peak of the waveform to the trough. A cycle is the amount of time it takes the waveform to go from one amplitude all the way through its amplitude changes until it reaches the same amplitude again. The frequency of the waveform is how many cycles it goes through each second, where 1 Hz is 1 cycle per second. That is, a waveform at 1000 Hz goes through 1000 cycles every second. When two or more sound waves meet, their amplitudes add to and subtract from each other. If the peaks and troughs of the two waveforms line up, they are said to be in phase. In this situation, each peak adds to the peak in the other waveform, and each trough subtracts from the other troughs, resulting in a waveform that has twice the amplitude of either individual waveform. Sometimes the peaks of one waveform match up with the troughs of the other waveform. The peaks and the troughs will cancel each other out, resulting in no waveform at all. Such waveforms are said to be 180 degrees out of phase. In other cases, the waves are out of phase by some other amount. This will result in a more complicated waveform than either of the original waveforms, as the amplitude at each point along each waveform are added together. Two simple waves can make a complex wave file like this. Continuing to add waves will make a more and more complicated waveform. When you see music, voice, noise, or other complicated sound represented by a waveform, you are actually seeing the result of adding all the waves from each instrument together. A microphone works by converting the pressure waves of sound into changes in voltage on a wire. These changes in voltage match the pressure waves of the original sound. High pressure is represented by high voltage, and low pressure is represented by low voltage. Voltages travel down the microphone wire and can be recorded onto tape as changes in magnetic strength, or on vinyl records as changes in amplitude in the groove. A speaker works like a microphone in reverse, taking the voltage signals from a microphone or recording and vibrating to recreate the pressure wave. Everything discussed so far is known as analog audio. Unlike analog storage media like magnetic tape and vinyl records, computers store audio information digitally. In digital storage, the original waveform is broken up into individual samples. This is known as digitizing or sampling the audio, and is sometimes called the analog to digital conversion. The sampling rate defines how often a sample is taken. For example, CD quality sound has 44,100 samples for each second of the waveform. The higher the sampling rate, the closer the digital waveform will be to the original analog waveform. You can see the error caused by sampling. If the number of samples in this section of audio is doubled, the curve they represent comes closer to the original analog curve. The sampling rate limits the frequency range of the audio file, because in order to reproduce a given frequency, the sampling rate must be at least twice that frequency. For example, if the audio contains audible frequencies as high as 8,000 Hz, you will need a sample rate of 16,000 samples per second to represent this audio accurately in digital form. This calculation comes from the Nyquist theorem, and the highest frequency that can be reproduced by a given sample rate is known as the Nyquist frequency. CDs have a sample rate of 44,100 samples per second because human hearing can register frequencies slightly above 20 kHz. Just as the number of samples in each second of audio determines the resolution of the sampled audio, so does the resolution in the amplitude of each sample. Amplitude resolution is referred to as the bit depth. A bit is a computer term meaning a single number that can have a value of either 0 or 1. A single bit can represent two states, such as on and off. Two bits together can represent four different states. The bits can be 00, 10, 01, or 11. Each additional bit doubles the number of states that can be represented, so a third bit lets us represent 8 states, a fourth 16, and so on. The resolution in amplitude is just as important as the sampling resolution. When a waveform is sampled, each sample is assigned the amplitude value closest to the original analog wave. With a resolution of 2 bits, each sample can have one of only 4 possible amplitude positions. With 3-bit resolution, each sample has 8 possible amplitude values. Higher bit depth means a lower noise floor and higher fidelity. CD quality sound is 16-bit. Which means that each sample has 65,536 possible amplitude values. DVD quality sound is 24-bit, which means that each sample has 16,777,216 possible amplitude values. In summary, the process of sampling or digitizing starts with a pressure wave in the air. A mic converts this pressure wave into voltage variations. A digital to analog converter, such as a sound card, then samples the signal as the sample rate and bit depth you choose. Upon playback, a digital to analog converter, like your sound card again, reconstructs the waveform by connecting these samples together. When you record audio on your computer, Cool Edit tells the sound card to start the recording process and specifies what sampling rate and bit depth it should use. The hardware that the sound card uses determines the sample rates and bit depths that it is capable of recording. Your sound card probably has both line-in and microphone inputs through which it can accept analog signals. The sound card samples the audio at the specified sample rate and assigns each sample an amplitude value. Cool Edit stores each sample in sequence until you stop recording. Once you've recorded the audio, you can use Cool Edit to edit the audio or save it to disk as a file. When you play a file in Cool Edit, the process happens in reverse. Cool Edit tells the sound card that it is going to play a file and sends the samples to the sound card. The sound card reconstructs the original waveform and sends it out as an analog signal from the line-out port to your speakers. MIDI and digital audio are fundamentally different representations of sound. A digital audio file seeks to exactly represent an audio event, just like a tape recorder, whether it's a musical performance, a person talking, or any other sound. MIDI, on the other hand, is more like sheet music. MIDI files record information such as the note to be played, the instrument to play the note on, the pan and volume of that particular note, and so on. When a MIDI file is played back, The sound card takes this information and uses its synthesizer to recreate the note on the right instrument. Because every synthesizer sounds different, the MIDI file will sound different depending upon what sound card plays it back.
Bueno, ni tan así. En el pasado es verdad que el MIDI debía ser interpretado por el sintetizador interno de la placa de sonido, pero hoy por hoy el sintetizador puede ser un software que se ejecuta en la computadora. Y más que sintetizador hablamos de los instrumentos virtuales, que pueden ser sintetizadores o pueden estar basados en grabaciones a instrumentos reales, muestras de grabaciones a instrumentos reales, o sea, samples de grabaciones hechas a un instrumento cualquiera. No debe confundirse con el sample del que el video habla un poco más atrás. Una cosa es un instrumento basado en samples y otra cosa es el sample rate. Al principio esa diferencia puede ser un poco confusa, pero es necesario marcarla. Eso es todo por ahora, espero que les haya sido de mucha utilidad. Chau.